Good morning. Today we are looking at chapter 16, and chapter 16 is looking at sound. And in many ways, it's a continuation of chapter 15. In chapter 15, when we were looking at waves and wave motion, we often just refer to that as sound propagating through some kind of a medium. So let's take a look and see what we've got in this chapter. So here's a list of the topics that you can use as a reference. So let's start talking about some characteristics of sound. So the first thing I want to point out is, what is sound? And it's waves. Now it's waves, as we discussed in chapter 15, and I'm guessing when we went through chapter 15, for many of you, that there were a lot of misconceptions that you had about what we mean when we talk about waves in physics. So in any case, I guess I had that mantra about disturbance propagates through medium. So a disturbance that propagates through a medium, that's what we mean by a wave, and sound that's what sound is. So when we talk about sound, I guess more specifically we think in terms of things we can hear, specifically those disturbances that we can sense through our sense of hearing. So sound, waves, can travel through any kind of a medium, but not through a vacuum. As we found out back in chapter 15, wave motion actually is a result of motion of the medium. What we've done is we've set the medium into oscillations. We've set the medium into oscillations where they either create compressions or where they create transverse effects where we have displacements back and forth. And so it's some kind of a disturbance. Now here, they just got a list of different speeds. We saw these in chapter 15. We looked at the speed of air at 20 Celsius. What else did we look at? The speed of sound in air, speed of sound in water. What you can see here is in something like steel, these speeds go even much higher, 5,000 meters per second. So sound, it is the motion of the media, of the medium that we are, that the sound is propagating through. All right, when we talk about the speed of sound in air, it says here, I don't know if you guys learned this growing up, I did, it would say that this rule of thumb is that when you would see a flash of lightning, you would wait to hear the thunder. So the light travels so quickly, when you see lightning, even if it's quite distant away from you, you see that almost immediately. There's a very small time delay from the light reaching you. But sound is going to travel at a much lower speed. So sound is going to propagate at a low speed compared to the speed of light. So the speed of light is 3.0 10 to the 8th meters per second, and it's about 1,000,000 times faster than sound. What we saw for sound was this in air at 20 degrees Celsius, 343. All right, so here we go. 1 mile is 1,609 meters, roughly. And the time then would be the distance divided by the velocity. This is putting in the speed of light, and it tells us that the time would be, well, it's 5 microseconds. So if the lightning flash was a mile away for every mile distance, it would take light 5.36 microseconds to travel the mile. So, that's not zero, that's something. Now sound, for the very same distance, traveling at the speed of sound, would take 4.7 seconds. So that's pretty close to 5, right? If you count to 5, 1, 2, 3, 4, 5. That's enough time for sound to have traveled a mile, roughly. All right, it works. Let's think about sound. When we are listening to sound, the loudness of the sound is related to intensity. We'll see what that relationship is. Loudness is kind of a subjective experience. So it's not like I can tell you, I can describe how loud a sound sounds to me, but that's not measurable. It's not measurable in the sense of reproducibility. But what we can do is we can work in terms of intensity. If you remember last chapter we introduced that. We can talk about sound in terms of how many watts per square meter the sound is, and that gives us something that is measurable, that's reproducible. So loudness of the sound is related to intensity. Pitch is essentially frequency. Different frequencies we're going to experience as different pitch. Now, there is an audible range. There's a range of frequencies that we can hear, and they run from about 20 hertz to 20,000 hertz. Those are easy numbers to estimate. And the standard line is we can hear between 20 and 20,000, but with age, you lose the high frequency end of your hearing. So, there are probably high frequencies I just don't pick up anymore. Ultrasound. So if we're above 20,000 hertz, we refer to these frequencies as ultrasound. Now, the idea is we can't hear the ultrasound because our auditory system isn't set up to pick up those high frequencies. Similarly, there's infrasound. That's below 20 hertz. So hearing is pretty interesting, right? Because within the ear, you've got these channels inside there, and then there are these hair cells inside there that are looking for disturbances that are amplified. And then within that tube, there's a little tube that's kind of spiral, I guess, and that means that at different locations within the tube, different frequencies will resonate. They'll set up standing waves, very temporary standing waves, and the cells respond to that. So the cells, the little hair sticking out of the cell or whatever, will oscillate back and forth if there is a standing wave that gets set up at that location. So, hey, that's hearing, right? And then those cells are attached to neurons, and the neurons fire, and it gets processed in the brain, whatever that means, and we experience, we have a subjective experience of sound from that. All right, so here are those longitudinal waves that we talked about in the last chapter. Here's a region of compression, rarefaction, and compression, expansion, compression, expansion. And yeah, they've got a direction listed, so they're saying that this effect of a series of compressions are propagating in some direction. Now, what we can do is, all through chapter 15, we kept talking about disturbances, we kept talking about waves in terms of displacements, and now what we can show is that for these longitudinal waves, we can also represent them in terms of pressure. So there are formulas that are going to relate intensities in terms of displacement and displacement amplitudes, and in terms of pressure variations. So this graph is thinking in terms of how the pressure varies from one atmosphere. So if at equilibrium everything's at 1 atmosphere pressure, when the sound propagates through, some regions go a little higher and some a little lower as this propagates through. Now you can see these numbers. If we say that the ambient pressure is one atmosphere exactly, 1.0000, we can see an increase of 2 parts per 100,000 per 10,000, and a decrease. And you might be thinking, oh, that's probably not very loud. Those are really, really small variations in pressure. And actually what we're going to find is that this amount of variation in pressure is painfully loud. You know, this could be 120 decibels of sound level, and we'll go in and talk more about decibels and what they mean. So these very small disturbances, now this is in centimeters, so centimeters, millimeters, so this is looking like plus or minus 5 micrometers, you know, the distance, the thickness of a cell. You know, you say red blood cells are like 3 microns across or something. If you get the air molecules so that on average they're just shifting back and forth that amount, it's painfully loud. Okay, so we are really sensitive to these patterns of disturbances that get set up in the air. And again, here is a profile showing how the variations in pressure are being represented mathematically. So again, I think we talked at the beginning of chapter 15 about how dangerous the word wave is, because you know, sometimes people go, oh yeah, everything's waves, right? Everything's waves, and then they do this kind of stuff. And so we want to be really specific. There's nothing here really waving. What this is showing is the variations in pressure as we move along the propagation direction of the longitudinal disturbance, of the longitudinal wave. All right, here are some formulas. I don't know how much depth we're really going to go into with these. This is an intensity formula we actually derived back in chapter 15. So if you look at that, that's the intensity of a wave propagating through a region. We said that the intensity is proportional to the wave speed, the density of the material, the frequency of the disturbance, and the amplitude. And what we're showing here is that we can actually show that the amplitude of the disturbance can be related to variations in pressure. And we'll probably just go through those briefly. I left these slides in place just to show that the intensity can be represented not just in terms of amplitude, but also can be represented in terms of pressure variations. All right, here is, well, let's take a look at decibels, which are units we use to describe the loudness of sound. Kind of, you know, when someone says the sound is really loud, what does that mean? And what we find is the threshold of human hearing, this is kind of remarkable, has an intensity of 1 × 10⁻⁻12 watts per square meter. So here is the sound coming in, and I'm listening for it. I put myself in a really quiet room. Maybe I'm at the doctor's office, and they go, let's go ahead and give you a hearing test, and they put you in one of those soundproof rooms, and they put on the headphones, and you hear those really, really faint sounds. So that's what this would correspond to. So think of yourself back in the doctor's office getting a hearing test. Those very faintest sounds that you can hear correspond to about 1 trillionth of a joule per second spread out over a square meter. Now, I don't know about you guys, but my ears are nowhere near the size of a square meter, I think. I think they're smaller. And so it's just a tiny, tiny amount of energy. It's it's a fraction of a trillionth of a watt that you can hear. So now what does happen with hearing is you're very, very sensitive to these very faint sounds, but when something has 1 trillion times as much intensity, people don't say it sounds 1 trillion times louder. So people go, nah, that doesn't sound 1 trillion times louder. A conversation might be at 60, might be at what do they have listed here that we could use? If I'm listening to one conversation, and I can kind of judge how loud that sounds. Now if I go into a room where 10 conversations are going on, it sounds louder, but it doesn't sound 10 times as loud. At least that's what most people report. So rather than use intensity, and we'll use intensity plenty to represent how much energy is stored in the sound, but what we've done to provide more of a subjective scale where people report how loud things sound is we've taken the logarithm, the base 10 logarithm of these numbers, and converted that over into something we call decibels. So let's see how that works. Because it's a logarithm, this would be 12 powers of 10. The threshold of hearing, we actually designate at 0. So with logarithms, you may remember, logarithms are tricky. I'm very sympathetic about how tricky logarithms can be. If you remember how logarithms work, every time I multiply a number by 10, its logarithm goes up by 1. So this would be going up by 1 power of 10, this would be going up by 2, 3, 4, 5, 6, and then that would be what we call a bell, but we're actually using our decibels. So it's 1/10 of a bell, and that means that every time we go up in intensity by a factor of 10, somebody threw that intermediate value in there, every time the intensity goes up by 10, the decibels, we add 10. So adding 10 decibels means that the energy went up by a factor of 10. And that's how logarithms work. Now here's an interest, and we'll get to a formula to see that. But we want to throw this in right now. This shows the sensitivity of human hearing as a function of frequency. So it's not like, you know, across 20 to 20,000 hertz, it's not like our sensitivity is uniform. It's only in the region, in this region right here, between, you know, about 500 up to a few thousand, where the sensitivity is really the highest. And in fact, this is, you know, this is representing that at 1,000 hertz, typically people can hear down to 0 decibels. But a little higher frequency, if you go up to 2, 3, 4,000 hertz, you can actually hear at lower intensity, lower intensities, lower than 10 to the minus 12, those would actually be in negative decibels. Okay. Okay, I'm not sure what these phones are here. Just notice those. It looks to me like the numbers are they're just decibels that we're looking at. Okay, here's the formula. How does the formula work? What we do is we take the intensity of the sound, divide that through by a reference intensity, and for the reference, we use the threshold of hearing. So by using the threshold of hearing and using this formula, using the logarithm formula, that means that if the intensity is right at the threshold of hearing, that becomes a ratio of 1, and the log of 1 is 0. So that would be 0 decibels. Now, again, there's a factor of 10 out front to convert it from bells into decibels, which turn out to be more convenient. So let's say that, let's practice, let's do this first. No, I think everything's there, huh? So this is the formula in decibels. This is the symbol beta, and that's the reference intensity that we're going to work from. All right, what about the sound intensity on a street? So let's say that we're on a busy street, and the sound level, or the loudness that we're hearing, we gauge to be 75 decibels. What's the intensity? So here's how that works. Now I can take, this is the formula they gave us. Beta is equal to 10 times the base 10 logarithm. So make sure on your calculator you know where the base 10 logarithms are compared with the base E natural logs. This is the formula. So this is, intensity is going to be in watts per square meter. Those are standard units. These decibels really are unitless. They're just numbers. They don't really, if you notice, all the units canceled out right there. And so decibels are kind of an artificial unit that we've developed. Now the reference intensity is always going to be 1 times 10 to the minus 12 watts per square meter. I can put that in. And what I find then is that, actually let me turn the formula around first. What we're going to do is solve for the intensity, because in this problem, they've given us the number of decibels. They've given us the loudness. They've given us that as 75 decibels, which, just for reference, would be 7.5 bells. So 75 decibels, and then if I'm going to solve this equation, I'm going to divide both sides by 10, I get beta over 10, and then I'm going to exponentiate. So when I take this, 10 to this power, the logarithm will drop out. I'll have I over I naught. So the inverted formula is intensity equals reference intensity times 10 to the beta over 10. If beta is 0, if it's 0 decibels, then this becomes a factor of 1, and we are at reference intensity, if that's the case. Now, let's use this. So for the reference intensity, I'm going to plug in 1.0 10 to the minus 12 watts per square meter. And then over here, I'm going to plug in these 75 decibels and divide through by 10, which puts me at 7.5 bells. So what it's saying is this. I want to stop I want to stop at this step and say that the intensity is I naught, that's the reference, times some number of powers of 10. That's how logarithms work. How many powers of 10 am I looking at? Well, if it's 75 decibels, I'm looking at 7.5 powers of 10 above threshold. So that would put me at 10 to the 7.5. Now what that is it's 10 to the 7 times 10 to the 0.5. And that turns out to be 10 to the 7 times 10 to the 0.5, 3.16. So the intensity that corresponds to 75 decibels would be 3.16, 10 to the minus 5 watts per square meter. Okay. Yeah, that looks right. Just double checking. All right, what about a loudspeaker response? So we have some high quality speakers. Are they loudspeakers or are they just speakers? We have a high quality speaker advertised to reproduce at full volume frequencies. All the way, this speaker works between 30 hertz and 18,000 hertz, and it faithfully represents the loudness to within plus or minus 3 decibels. So over that entire frequency range, they're claiming that it'll get all the loudnesses correct. It will reproduce those at that level. What this really comes down to for us is, what does 3 decibels mean in terms of intensity? So let's try that out. What we can do is we can say, okay, I've got intensity 1, which is I naught 10 to the beta 1 over 10. Let's say we have a different intensity. So there are these 2 different intensities that we're considering. And this, I write down the formula again. Now, in order to compare differences in decibels, so what they told us was the difference in the number of decibels could be as large as 3. Well, what would a variation of 3 decibels mean in terms of intensity? And so for that, we're going to take a ratio of these 2 intensities. Differences in decibels correspond to ratios of intensities. So I'm going to take the ratio. The I naughts cancel out. 10 to the beta 2 divided by 10 to the beta 1 becomes beta 2 minus beta 1, both over 10. And that says that, oh look, a difference in decibels divided by 10, 10 to that power gives us a ratio of intensities. So if I were to have something larger by just 3 decibels, and that's what they're saying with this speaker, let's say that the speaker is too high by 3 decibels for a certain range of frequencies certain range of pitches. The I2 over I1 then, for that, would be a factor of 2. Actually, just coincidentally, 2.00. So it's a factor of 2. 3 decibels means twice the intensity. So that, to me, seems pretty significant for this speaker. But remember, subjectively, that's not the way that we experience sound. So our sense of sound is not fine-tuned so much to intensities as it is to the decibel scale. Okay, so just one more reminder here of what this formula we just derived would look like. Here's a ratio of intensities, and I plotted this. So, and this is just, it's just a mathematical equation representing a base 10 logarithmic function. But what we are seeing is that a difference in decibels of 3 almost is exactly a factor of 2. And that means if we do another 3 decibels, now we have 6 decibels, that would be 2 factors of 2. That lines up pretty well with 4. And another 3 decibels plus 3 decibels plus 3 decibels would be 9. But each of those 3 decibels represents a doubling of the intensity. So that would be 2 times 2 times 2. That would be 8 times the intensity. So that's not a bad graph to stare at, too, to kind of think about how decibels and intensity ratios are related. All right, one more example with the sound loudness. Let's say that we have some trumpet players, and an individual trumpet standing there playing, we measured that at 75 decibels. Now all three of them play together. 3 equally trumpet players join. Wait, doesn't that make 4 trumpets? I think I miscounted. I totally miscounted. It says 3 join in. I thought there were a total of 3. Okay, sorry about that. I have to read the problems more carefully. All right, so we're going to say this. We're going to say that we have 75 decibels. Now, we know that corresponds, each trumpet player is going to have an intensity then of 3.16 10 to the minus 5 watts per square meter, following our formula. What we're going to do is we're going to triple the intensity. So if I got 3 trumpet players, then I can add the intensities. I cannot add the decibels. The decibels don't add. I can't take 75 plus 75 plus 75. That's not the way the decibel scale works. Now it actually is 3 times as much energy, so the intensity will be 3 times as large, and that becomes 9.49 10 to the minus 5 watts per square meter. So that's 3 of them together. And then, so I had to convert into intensity, multiply the intensity by 3, and then convert back into decibels. And so when I did that, I converted back into decibels, I got 79.8 decibels, which is basically that's very close to being 5 decibels. Is that right? 4.7. Okay, so I kept some more significant figures here. I actually got 4.77, so a little less than 5 decibels. Now the intensity went up by a factor of 3. Let's go back and see if we can use that graph again. So on the graph then, what we're seeing is if I have 3 trumpet players, that should correspond, to a little less than 5 decibels. So that worked. Now there were really supposed to be 4 trumpet players, I think, if I'd read the problem carefully. Now if there's 4 trumpet players, that would mean that the intensity went up by a factor of 4. And so if I go up to a factor of 4 and come across on my graph, that would have been 6 decibels. So if I'd done the problem correctly, the sound level should have gone up by 6 decibels. It should be at 81. So this is kind of interesting though, right? I was at 75 decibels with 1 trumpet. and now I have 3 trumpets. Shouldn't that be a much bigger number? No, it only went up to 80. Okay, so it's not that much larger. The loudness has not gone up by that much. The loudness as measured in decibels. Okay, we also looked at intensity of sound. Or we looked at intensity back in chapter 15, and specifically that the intensity would drop off with distance, 1 over r squared. Now I want to emphasize this lower part here. I've mentioned this a few times, that the formulas that we're using are ignoring damping effects. They're saying that once we've generated that energy and that wave is propagating away, that all of the energy remains in the wave. So even though the intensity drops off as it spreads out in different directions, the drop off in intensity is due to the spherically spreading effect. That's what we're considering. What's being left out is, in addition to the spherically spreading effect, there's also a damping effect where some of the energy just becomes thermal. So that perfect profile is not necessarily maintained, and we'll end up with just kind of random motion of the air molecules instead. But we're going to stick with it. It's a good approximation over short distances. And so let's say we have a jet engine, and the sound is spreading out uniformly in all directions. There is a worker who is standing with good protective earwear 30 meters from the jet engine. And without those, I mean, the sound loudness is 140 decibels. So it's a good thing the person has those ear protective gear on. Now, what would happen if we came 10 times farther away? And it says ignore reflections from the ground, which basically means assume that the sound propagates uniformly in all directions. So for that, here's that same picture. So here is the central source of the sound. This time the central source is a jet engine. And here is the intensity at 30 meters, and here is the intensity 10 times as far away. And I feel like this is pretty much a duplicate of the problem that we saw back in chapter 15. Here are the intensity formulas for those 2 different locations. And remember, the key feature here is that the power of the sound source is the same. The power represents what's happening at the location of the sound source. So that's going to be a certain amount of power. Now, I don't think I calculated the total power this time. I could have. I kind of wish I would have. Anyway, we're going to say we're going to measure this at 30 meters and 300, and the measurement at 30 is 140 decibels. What will happen if I go 10 times farther away? So what's going to happen with the ratio of intensities? I can represent the ratio of intensity 2 compared with intensity 1 by using these 2 formulas. The power will drop out. The 4 pi's will drop out, and I'll be left with a ratio of 2 distances. Remember the R1 and the R2 here. I know there are radiuses also, but let's think of them as distances. So R1 squared, distance 1 squared, divided by distance 2 squared, that would be 30 meters divided by 300, that's 1/10, and that would be squared. So if I move 10 times farther away, this predicts that the intensity should drop off by a factor of 1 over 10 squared, which would be 1/100th. So the intensity is going to drop down to 1/100th of what it was before. Now, if I use the formula of delta B of the 2 different intensities, is 10 times the logarithm of I2 over I1. So now what we've got is we've got 2 different intensities that we're comparing, and the reference intensity, I0, has dropped out of the equation. So we don't have to use the reference intensity for this, because we're going to be comparing the difference between these 2. Now, that difference was a factor of 100. taking the logarithm of 100th, that's going to give me a factor of -2. 100th represents -2 powers of 10. So that would be a difference in decibels of 20 decibels. So every time the intensity drops by a factor of 10, the decibels are going to drop by 10 decibels. And we didn't drop by 10, we dropped by 100. That's 2 powers of 10, so that's going to be -20 decibels. So even at 300 meters away, the sound would be 120 decibels. Now, we talked about damping. Over a 30-meter distance, damping is not a huge effect, but once we get out to hundreds of meters, the damping effect is going to be fairly significant. Okay, so it could be that we'll be lower than the 120 decibels at a distance of 300 meters. Okay. All right, this example is just taking a look at the displacements. There were some formulas that they had given us before. We're going to plug some numbers in and just see what that would be. In part A, they're talking about the threshold of hearing at 1,000 hertz. Now, if you remember from that graph that we looked at earlier, if we are at the threshold of hearing at 1,000 hertz, that's defined to be 0 decibels, and that is 1.0, 10 to the minus 12 watts per square meter. So we're gonna bring back this formula. This is something we derived in chapter 15. So let's come back and use the formula that we derived and plug some stuff into it. So we can put in omega is equal to 2 pi times the frequency here. The frequency was 1,000 hertz, and so the omega value is 6,283 radians per second. Now from that, what we can do is solve for the amplitude. So I've got a squared is 2 times I divided by the density divided by omega squared divided by the wave speed. So 2 times I, that's the threshold of hearing, and the density of air, 1.20 kilograms per meter squared. There is the omega squared, and there is the wave speed. Now when we do all those numbers, and then we take a square root. And when we calculate that, it works out to be for the threshold of hearing. Remember, you're back in the doctor's office, you've got the headphones on, those really, really faint sounds. The amplitude is about 11 picometers, where a picometer is a trillionth of a meter, 10 to the minus 12. All right. Now, the size of an atom is about 200 picometers. So, you know, a molecule of nitrogen or oxygen in the air might have a size of a few hundred picometers. How much compression are we getting? And the oscillations, amplitude that we're getting back and forth, is about 11 picometers, and we can hear that. So you can see that 11 picometers is pretty small. It's much smaller than the diameter of a molecule. All right, that they've moved. Now, I had to do a comparison here. At a louder sound, let's go up to something 80 decibels. That would be an intensity of 10 to the minus 4. Even at 80 decibels, which is a fairly loud sound. If you're in a loud room with lots of conversations going on, maybe that's 80 decibels. In that case, the amplitudes actually of the oscillation are going to be larger by 10,000. Okay, so there we're going to have a tenth of a micron of variation. And again, you know, red blood cells are what, 2 or 3 microns across. So you're still, the amplitudes here are still really small. So, you know, if you think back to that first example when we looked at the pressure variations and the amplitudes, it doesn't take much. You know, this was less than a micron, and we're at 80 decibels. Okay, in terms of pressure variations, now this is a formula that they've derived. We're not going to go back and derive it. but the pressure variations can be related to intensity, and so I plugged the numbers in for that. And for the pressure variations at threshold, we're seeing 2 times 10 to the minus 5 pascals. Now, atmospheric pressure is 101,000 pascals, and if we see variations of 20 millionths of a pascal, that's audible. If there are no other sounds around, we can pick that up. So just amazing. And then again, the pressure variations at 80 decibels would be 10,000 times larger, and so that would give us, I mean, it's still kind of a fraction of a pascal. If we went up to 120 decibels, that's, 4 additional power, that would be 100 times more. That would be 1,000,000 times more of amplitude. That would give us about variations of 20 pascals. So at the threshold of painful, the painful threshold where it hurts, it's so loud, the variations in pressure are about 20 pascals. All right, what about musical instruments? So let's get started with some of this. We do want to take a look at some physics of musical instruments, as long as we've got a chapter on sound. Musical instruments produce sounds. We have string instruments, which are transverse disturbances, transverse waves, transverse standing waves, set up on a string that's one-dimensional. We have drums that are membranes, that's a two-dimensional standing waves that get set up on a drum. We have also in woodwinds, brass instruments and woodwinds, we have oscillating air columns. We have, these are all standing wave patterns. So the vibrations, are set up initially by creating some kind of a disturbance. We pluck the string, we strike the drum head, we blow air through a tube, and all of those set up standing waves on the different instruments. And then the vibrations that are set up, these different wave patterns, standing wave patterns that are set up, are in contact with the air, and that energy gets transferred into the air and it propagates as sound, and we hear it. So let's take a look and see what we've got for these musical instruments. And so here is a table of frequencies. Here's a table of frequencies that we can work from, and maybe you guys are familiar with, here is an octave played, let's say this is on the piano. This is probably, thinking in terms of a piano is probably the easier way to visualize this, although if you want to visualize this on a guitar string or something, that works fine. If we go through a scale where we don't skip any of the notes, so on a piano, pianos have been designed to play certain frequencies. Now, the certain pattern of frequencies we see on the piano or on a guitar or whatever have developed over thousands and thousands of years, and they're variations. There are certain patterns of frequencies that get used in different types of music, but a standard piano would be tuned in a manner where here is C, C sharp, D, D sharp, E, F, F sharp, G, G sharp, A sharp, B, C. This C is referred to as being an octave higher. Now, what does that mean? Well, surprisingly, an octave higher means we have doubled the frequency. Now, it turns out that doubling the frequency means that there's a ratio of 1 to 2 between those two frequencies, and that has a certain sound to it. So we actually think of it as, I can start with these sets of frequencies, these sets of pitches, and then when I get to here, I've doubled it, and then I can go back and double all these, and it will sound kind of like I'm repeating the same pattern at a higher set of frequencies, which are all doubled. And that produces a certain subjective effect. That has a certain, we hear that as a certain type of pattern. So this doubling of frequencies is kind of interesting, that the scales are based on those. All right, we're gonna ask, how did they generate these numbers? Where did these frequencies come from? I know that if I go through 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, what we call half steps. They're not called full steps, these are called half steps. If I go through 12 half steps in terms of frequency, eventually that's going to lead to doubling the frequency. But what are the individual intervals determined by? And let's take a look. So it turns out that the octave, which actually means 8, we can go back and talk about that too, but increasing the pitch by an octave means that we're going to double the frequency. Now they've used, in their diagram, they went from C to the octave, 1 octave higher, and that's because if you're looking at a piano, you know, middle C is considered kind of the starting point, kind of at the center of all the keys. But in terms of frequency, it's actually maybe better to start with an A, because officially the A above middle C is designated to be 440 hertz. That's kind of an official tuning that people work from. If you've got apps on your, if you've got apps on your phone that you use to tune, a guitar or some instrument that you play, chances are that's set so that when you're tuning to A, it's right at 440 hertz. Okay. In fact, some apps will have a 440 hertz sound that plays to designate the reference. So that's what I did. I did an octave, but I did it starting at A and ending at A. Now, officially, this A is supposed to be at 440, so officially, this A is supposed to be at 220. Those are supposed to be the exact references. Now, the way we're going to get to doubling the frequency in 12, what we call half steps, is to make each frequency of each note larger than the note just before it by 2 to the 1/12th power. So what we want to do is we want to have the same factor for each one. So if I start at any note along here, the nth note, and then I go to the frequency just above it, that's going to be larger by 2 to the 1/12th, which works out to be 1.05946 something something something. Now, why are we using 2 to the 1/12th? Well, the idea is by the time I have boosted the frequency by this number 12 times, if I take 2 to the 12th and I apply that 12 times as a factor, I get a factor of 2. So what this tuning formula does for us is if I take this number and I go through 12 half steps, then I end up with a perfect octave. I end up with a perfect doubling of the frequency. Now, that's kind of interesting. So we'll probably come back to this and look at some of the frequencies. I do just want to point out, though, that this 440 is exact, the 220 is exact. These other frequencies I've rounded. Now, they're not supposed to be rounded. They're supposed to follow this exact formula if they're in what's called the well-tempered scale. Now, it turns out there's a history to this well-tempered scale, and that is, hundreds of years ago, it used to be that you would tune to get certain ratios of frequencies, certain exact ratios. So this, for example, is at 330, but it's not exactly at 330. It's a little bit away from 330. Really good musicians could tell that ratio, that 330, did not have a 3:2 ratio with the A's. But what people found was if you tune the instrument to play in just one key, then if you move to a higher key or a lower key and tried playing the same song, pitched a little higher or lower, it sounded different. So using this well-tempered approach means that whatever key you play a song in, whether you choose to play it lower, using a lower set of frequencies, or the same pattern but repeated at a higher set of frequencies, it has all the same relative pitches, all the same relative frequencies, and that makes it sound the same. So that's what the well-tempered scale has done for us. All right, here we've got, we're back at standing waves. So we're first of all going to be looking at string instruments. And so here we are back with standing waves, same thing we looked at in chapter 15. And I've got my first harmonic, I got my second harmonic, I got a third harmonic. Those are the harmonics here that we have set up. And what we found back there was the first harmonic will have some fundamental frequency that we can determine by tensioning the string, choosing a string with a certain density to it, and determining the length of the string. So length of the string, mass of the string, or density of the string, and tension is going to determine the pitch. And the second harmonic will have twice that value, and the third harmonic will have 3 times. Now what that means is that, let's say that I've got a guitar string, and the guitar string, I've tuned it to an A. If this is vibrating, if the frequency here is 220 hertz, this is 440, and this is 660. So these are going to be multiples of whatever that fundamental frequency is. Let me go back and say this then. So if, let's say that we have a guitar string and it's been tuned to 110 hertz. Now 110 hertz would be an A 1 octave lower. That guitar string tuned to 110 is also going to be capable of playing the 220 hertz, the 330 hertz, the 440 hertz, the 550 hertz, the 660, the 770. They're going to be all these overtones. And depending on how I set that guitar string into vibration, I will get a superposition of different frequencies on that guitar. So that's kind of interesting too, when our intention, let's say, is to play the first harmonic, but along with that we'll get contributions of these higher harmonics happening at the same time. All right, so here is the guitar. We've built the guitar. We've built the guitar so that the strings have a certain length, they have a certain density, and they've been tightened to a certain tension, and so we've got a certain pitch. What are the different frets on the guitar doing? I know that I've got different strings. You know, I have 6 different strings on the guitar. They have each been tuned to a different pitch, to a different frequency. But when I push down and on one of the frets, what is that doing? And it's shortening the length. So if I shorten the length of a string, that is going to raise the pitch. So if you go back and look at the wavelengths and the wave speeds and how that's related to frequency, shortening the length will shorten the wavelength. Shortening the length of the string will shorten the wavelength. And that will result in a higher pitch. Just because the string has been shortened, the string will oscillate back and forth at a higher frequency as a result of that. So there you go. This turns out it's a class on, this is an introductory class to playing the guitar. That's probably a good place to take a break, so let me go ahead and do that. And then we will come back and look at the rest of the chapter. Oh yeah, good time to stop.